Hello, I'm John Wallace, Senior Editor at Laser Focus World. Today, I'll be doing what we are calling a quick chat, which is a type of interview developed by us and our parent company, Endeavor Business Media, in which we talk with an experienced person in the area of optics and photonics who can supply practical knowledge for our audience to use as a guide for their own commercial or academic R&D efforts. Today's guest is Christopher Boucher, a technical product manager at COMSOL. COMSOL produces simulation software that has numerous uses in optics and photonics. They're adding applications all the time as they develop their software. And I'd like to note that this interview today is the first of 2 interviews with Chris. This first interview is an overview of COMSOL and its software, while the second interview will delve into the specifics. Welcome, Chris.
Hey, John. Thanks for having me today.
Good to have you. So to start off, for those who don't know a lot about COMSOL, could you give a summary of the COMSOL Multiphysics software, how it's structured, and what it does?
Absolutely, John. So about simulation software in general, the main idea is that when you have a design that you're either working on for the first time or possibly trying to improve on an existing design, or even just running diagnostics to find out why a given design doesn't work as well as you expect, the idea behind simulation is that you can cut down on the time and effort that you have to expend in the lab working on prototypes, for example, by creating and testing your design virtually. So in the COMSOL software that I work on, you can load in a CAD geometry. You can define any kinds of physics equations to solve on that CAD geometry. You can solve those equations. You can post-process or visualize the results in any number of different ways, and then export the results if you want to. So simulation in general is just a big time and effort and hence money saver. The fewer prototypes that you have to construct, the more time and money you can ultimately save. And another really good perk of simulation is that you can sort of look inside of an object in ways that you can't look inside of a real world physical object. So for example, if you're doing analysis of electromagnetic wave propagation, then you can look inside and see the electromagnetic, you can look at the electric field amplitude at any point in space that you want to. And it's very easy. So with COMSOL in particular, what I really love about it is versatility. We have a number of different packages for physics equations in very diverse application areas like thermal analysis, fluid flow. When it comes to optics in particular, we even have a number of tools for, say, low and high frequency optics. So I think that the versatility here is a real strength, and and the ease of use too. If you're going to be using a simulation tool, you want it to be easy to use because saving time is the whole point in the first place.
Okay, so why would one want to do optical simulation? What would you get from it?
So with optical simulation, then it depends on exactly what kind of design that you're working on, but what I work on more often than not is ray optic simulation. So I'm typically looking at the way that light rays are going to interact with some system of lenses or mirrors or obstructions and so on. And some of the things that people are especially interested in looking at these ray optic simulations would be the optical performance of your lens system, for example. And you might also be interested in how this optical performance is affected by things like structural deformation in your system, or perhaps temperature changes. You'll have things like the lenses might expand when they're heated, or their refractive indices might even change when they're heated. And these are all factors that COMSOL can take into account. So we get this very complete real world understanding of the system by combining all these different kinds of phenomena into one package. And you can even extend your analysis to do things like optimization or sensitivity analysis. So if you can change certain parameters of your design, like the distance between 2 lenses, for example, then you can program the model to automatically find the optimal distance for some figure of merit that you can define.
Okay, at this point, it might be good to summarize what types of optical simulation COMSOL can do.
Sure thing. When we talk about optical simulation, the really big divide is what we call optical size. So this is the ratio between the geometry size and the wavelength of the light that you're modeling. Now I say light, but it could actually be any kind of electromagnetic radiation. So it could be infrared, it could be ultraviolet, it could be radio propagation, and so on. Now, there are different types of numerical analysis that you can do when the wavelength is very, very small relative to the optical size, relative to the geometry size, and other types of analysis that are more appropriate just when the wavelength is about the same as the geometry size. So that's the big divide that you have to look at. And we break this into what we call ray optics analysis for objects where the wavelength is much smaller. And we have other methods that we call frequency domain electromagnetics and the beam envelopes method. And these are approaches that are very accurate, and they don't make the same approximations that ray optics does, but they're only really usable when you're dealing with something that is wavelength size. So imagine the cross section of a single mode optical fiber or a waveguide, or if you're looking at the scattering of light by just one piece of a much larger structure, then these might be examples where wave optics would be a better choice.
Mm-hmm. How accurate can these simulations be? I mean, you mentioned different types of simulations. How accurate are can they be?
Well, with ray optic simulation, then there are certain approximations that come into it. So for example, with our ray optics module, our ray optics tool, then we're assuming that the rays don't have any kind of coherence relationship with each other. So if you fire off a bunch of rays and then they cross paths, then you're not going to actually see the rays interfere constructively or destructively. And similarly, if a ray just barely misses an object in your geometry, then you don't actually see diffraction effects or anything like that. So these are due to the kinds of approximations that we make in using a ray optics approach. Now, on the other hand, with one of these smaller optical size approaches like electromagnetic waves in the frequency domain, we're using a method called the finite element method. And this breaks your geometry up into little pieces called elements and then solves the equation on these elements. So the finer you make this mesh and the smaller you make these elements, in general, the more accurate your solution can be. So when engineers are working on simulation, they always have this choice between, do I want to expend a lot of computational resources to have a very fine mesh and use up a lot of memory, but I get a more accurate solution? So they try to find the sweet spot where they get a solution that's accurate enough, but doesn't take too long to solve or doesn't consume too much memory. A very common practice is to start by solving your problem using a pretty coarse mesh, so you get an approximate solution, and then you gradually refine that solution until you see that it only changes within some tolerance that you'll allow. And we call this a mesh refinement study. So these are very common in practice, and it's a very widely recommended practice for engineers working in simulation.
I think for those in our audience who have not done this type of simulation at all, but who might want to try, at what point would they decide to do a simulation like this? I mean, what would drive them to do that?
Well, the main situations where I could see somebody wanting to do a simulation are you're trying to develop some new product and you want to predict how this product is going to work before you start producing it. Or you already have a prototype of some new product or some new system that you're working on, but you want to improve upon it, or you want to see why it behaves the way that it does. So we say that simulation can be used to plan, to optimize, or for diagnostics. And another element of simulation is that it helps you understand. So if you really want to understand more deeply why something's behaving the way it does, then one tool in your toolbox is to construct it virtually. And because you can probe into the solution and look at things like fields at any point in your design, then it becomes easier to understand in a way that you might not have before. Now, the one thing I'm not trying to say is I'm not trying to say that simulation replaces prototyping or that simulation replaces experiment, because I think there's always going to be a place for experiments and for prototyping in engineering design. However, I do believe that creating a simulation can reduce the number of experiments that you have to run or reduce the number of prototypes that you have to build to get a design that meets all of your requirements.
What kind of resources do people have to learn more about COMSOL? Where can they go?
Well, our website, COMSOL.com, has a lot of different types of resource, and this includes blog posts, it includes a video series, links to models. When you download the software, you can also download a library containing a lot of example models that show you how you can work in different areas. And these example models have instructions that show you how to set them up. Other really useful resources are looking for webinars or web workshops that we are giving online regularly these days. Looking for a COMSOL conference in your area. The conference is actually going to be virtual this year too. And ultimately just contacting somebody at COMSOL, and if you're really determined to start simulating, contact somebody at COMSOL and say that you're interested in trying it out.
Okay, well, thank you, Chris. This concludes our first quick chat. Our second quick chat will delve into the specifics of COMSOL as it relates to optics and photonics, and how you can use multiphysics simulation to not only model your optics, but your thermal, your mechanical, and I mean, you can even model chemical. I'm not sure you'd have to, but this is one of the capabilities of COMSOL. So on behalf of Laser Focus and Endeavor Business Media, we thank you for joining us, and be sure to look for the second quick chat with Chris Boucher.